Hey folks, we got another example of using Gauss's law to calculate the electric field. This time we're going to look inside a long a line of charge, an insulator, like imagine a plastic cylinder or something like that. Now I'll make a note on the previous example that we did. When we did a long line of charge, if you're outside the line of charge, you get this equation, 2k lambda over r for the electric field. But notice when r approaches 0, E would approach infinity, and that's not correct. So once we start digging into this line of charge, something else is going to happen. So again, we're assuming that the line of charge is an insulator, meaning let's say it's made of plastic, and I'll kind of draw this out here. So imagine here's our cylinder, okay? And it's made of something such that it's solid and the charge is uniformly distributed throughout that solid cylinder, okay? So we're going to figure out what the electric field is inside and outside the cylinder. Now, in this case, since it's a volume that they're giving us, they're going to usually give us a charge volume density rho. So remember the definition of that is Q divided by V, or dQ divided by dV, okay, dQ dV. So that's the volume charge density that we're going to use for this one. So we'll start with inside, okay? Okay, so let's say I wanted to know the electric field, I don't know, somewhere in the meat of this thing like there, okay? And we're going to use Gauss's law, so I'll write that out. Now again, we're going to try not to have to integrate here if we can help it. So we get the double integral E dot dA equals Qn over epsilon naught. Well, the shape we're going to draw is a concentric cylinder with our main cylinder, okay? So it's going to look like that. Okay, it's centered at the cylinder. This will be the radius. Some other things that you would be given. The radius of the cylinder itself we'll call capital R, okay? For our little cylinder that we just drew, our Gaussian surface, we'll call the height of it, you can call it anything you want. I'll call it L, but you can call it anything you want. All right, so what's going to happen here is electric field lines are going to be outward. Okay, so they're only going to leave the lateral face of that red cylinder. They're not going to leave the top or bottom of that cylinder, so all I'm worried about is the lateral face. So our equation here, we don't have to integrate because that field is perpendicular to that little red cylinder at all points and the same strength along all points. So you end up with E times, what's the lateral area of that cylinder? Well, it'd be 2 pi r L, okay, equals Qn. So there I got to do a little work. Well, I'm going to use this to figure out Qn. So Qn is going to equal rho times the volume of that red garbage can. What's the volume of that red garbage can? Well, it's the base times the height. The base is pi r squared and the height is L. Okay, so that's going to be our Qn. So we got rho pi r squared L divided by epsilon naught. And thankfully, a lot of stuff cancels out here. For instance, the height of that little garbage can doesn't matter. One of the radii cancels out, and even our pi cancels out. And we get the electric field on the inside of this thing is equal to rho times r over 2 times epsilon naught. Okay. So you'll notice that's a linear function. It's 0 at the center. If I'm at the dead center of this thing, the electric field's 0 because all the fields around me are going to cancel out. And as I go outward from the cylinder, it's going to increase, okay? Now, when I get outside the cylinder, my electric field should look like a similar equation to what I got before, okay? So it should be an inverse. It should be something over r. The only difference here is I don't have a lambda anymore. I have a rho, okay? So that's going to show up in my equation. So I'm going to actually redraw this picture here for the outside. So I'll do that really quick. So here's our solid cylinder of charge, okay? And now our garbage can is going to be on the outside of this thing, like so. Okay, so we got that, like that, okay? And then it looks kind of like that. All right, so, and again, it still has a radius r. And we're still using, the left-hand side of Gauss's law is going to look exactly the same. It's going to be E times 2 pi RL. So again, this has got a height L. So we got E times 2 pi little r L, okay, equals, now this time Qn is going to be different. Okay. How much charge did we capture inside this red cylinder? Okay, well, we're going to use Qn is equal to rho times volume again. But what do I plug in for volume this time? Well, I've captured this much. I've captured this much. I've captured what's in, I'll kind of mark it off here. We've captured that part of the green cylinder. So what's the volume of that part of the green cylinder? Okay, well, it's the base, which is pi times this radius, the radius of the cylinder, so big R squared, okay, times the height, which is L. Okay, so you got to be careful on which volume you use. How much charge did I actually capture? It's not the volume of the red cylinder, it's the volume of the charge that I've actually captured inside that red cylinder. So that's going to be our Q in here. So we got rho pi big R squared L over epsilon naught. And again, a couple things will cancel here. The pi cancels, the L cancels. It doesn't matter how high the garbage can I use is. And that's pretty much it. And I get E on the outside is equal to rho big R squared, which is a constant, okay, over 2 epsilon naught, and then there is our R. So there's our inverse. Okay, so that's the electric field outside this thing. Again, it's an inverse function. It looks a little different because we used a rho, a volume charge density, instead of a lambda, a line charge density. But otherwise, it's the same kind of equation. If I were to graph the strength of the electric field over distance, point of interest would be the radius of the cylinder. On the outside, I've got the inverse function, which is this one here, okay. On the inside, I've got my linear function, which is this one here, and I'll rewrite that down here. It's got rho r over 2 epsilon naught, rho r over 2 epsilon naught. Now notice if I plug in little r equals big R, which is the maximum here, the maximum electric field happens at the surface, okay, of this cylinder. These two functions will give me the same answer. So that's one thing to check. These two functions at that value should give me the same answer. The max electric field at that point is rho big R over 2 epsilon naught. Both equations give me that when I plug in big R, okay? So again, this problem is a little different than the last one in that we had a volume charge density because we had a volume instead of a line charge density. But on the outside of this thing, we still get the same kind of equation. It's still an inverse. It just looks a little different because we got a rho instead of a lambda. All right, I hope that was helpful, and thank you very much.